So how do we get a standing wave? Now the answer is actually going to be hold down one end or both ends of a string and vibrate or shake it at special frequencies. That's actually what we're going to do. But mathematically, we can think about it as two traveling waves that are going in, opposite directions, right? One to the right, one to the left, but they're going to share wavelength, which has to do with sharing a frequency. And because they're on the same string, or whatever your material is, they're going to share a velocity. So that's how we're actually going to make them. The book goes through a little bit of the math of what that looks like, and we're not going to worry too much about that, but let's at least think through how we can use superposition to think about how we get a standing wave from two traveling waves, where again, for simplicity, we're just going to assume that they're sinusoidal. So this is a little tricky to really look at and understand, but we have three different things we're looking at. The blue wave is our standing wave, and that is being made out of two traveling waves. We have a left moving wave, so that's our left moving wave, and we have a rightward traveling wave. So you can watch the location of the peak, keeping in mind that the dot here doesn't correspond to just a point on the string, but the location of the peak. So we see that on our red wave, the peak is moving to the right. On our green wave, the peak is moving to the left. But then we can watch a point on the blue standing wave, and we see that the peak stays in one location. Now in this case, the entire wave is 0. So how do we get there? This is where we need to use superposition. And again, it can be a little bit helpful, I find, to try to draw that equilibrium line. I would just encourage you, whenever you're drawing waves, to draw that equilibrium line. It's a little bit trickier to do it when the waves are already drawn. So we're drawing that equilibrium line. And so for instance, in this case, our two traveling waves align. And so your standing wave is just going to be twice what each of the wave is. Now if we go down here, notice that there are certain points where one wave is equally down and the other one is equally up. So our standing wave at that point is 0. Other places, both waves are up, and so that is going to be the maximum of our standing wave. You add them up. Here, they're both down, and so you have your maximally negative wave. There's a different moment in time where these waves are exactly opposite of one another. So this is summing a positive and a negative number that is equal magnitude but opposite sign at every single point, and so that's why our standing wave is 0. So again, looking through this, you can hopefully see that for every single position, if you sum the two traveling waves, you get the corresponding point on the standing wave. So sum the traveling waves, get the standing wave. This is just superposition. So mathematically, we can use that later to get what the functional form will look like, but conceptually, this is what's going on. Again, in problems, we're not going to create standing waves this way, but another reason that we think about it this way is frequently what happens is that you have, for instance, your string that's tied here. We're going to send our wave this way, but then it reflects when it gets here. So if it keeps going, and this is your reflection, well, and even though I drew it very poorly, these would have the same wavelength. So one of the ways you get this scenario is by imagining a wave reflecting off a fixed end. And if, for instance, I tie down one end of a string and I start shaking it at one end, that's what you're doing, and hence you'll get a standing wave if you're shaking it at one of the correct frequencies to actually get standing waves. So this is now then a portion of the entire cycle, but hopefully showing a little more clearly what's going on. So here's our standing wave picture that we previously looked at, and then here's just a portion of what we looked at before. So the blue line here is identical to the blue line here. And it's a little bit helpful to notice that our line here corresponds to that line and so on. So there's going to be specific times where our two traveling waves line up. You have your maxima values of amplitude. Other times where they cancel and you get zero amplitude there. So we can think a little bit about the math, and I keep mentioning that there's special frequencies where you get standing waves. In a subsequent section, we're going to think about that more explicitly, but I do want to point out that that is going to be something that happens.